Howdy, and welcome to yet another review video. How exciting. And this sounds silly, but I'll say it again. It sounds silly because I have said it again, and it'll say silly as I say it again. And that is, I don't know if you'll learn anything from this video, but it will remind you of what you've forgotten, I hope. Equilibrium. We have spent, golly, like 6 weeks, 7 weeks, 2 months almost studying equilibrium. Our first chapter, we talked about general equilibrium and how I have a reversible reaction forwards and backwards, or the rate of the forwards and the rate of the backwards are equal. I may have a whole lot of this or a whole lot of this, but aside from that fact, the amount of forward and backward is equal, although that's hard to identify and measure sometimes. But it's easy to write a constant. It's called the law of mass action, or the rules for writing an equilibrium constant expression. And you're expected to know that you always put the products on the top and the reactants on the bottom. And contrary to what we told you in the kinetics chapter, where you absolutely positively cannot place a stoichiometric coefficient as a power on that concentration unless it's an elementary step, in this chapter we're telling you that you should do it. It's the rule. So if I have one of these, two of these, and three of these, and four of these, or whatever, that's a 1, that's a 2, that's a 3, that's a 4. This works for not only molar concentrations, but also pressures of gases. In just about any unit you might like to choose, it should work out pretty well. And so, what does that mean? Oh, I know what it means. If I have a whole bunch of this, my constant will be big. If I have a whole bunch of this and very little of this. But if I had a whole bunch of this and very little of this, and that means there's a whole bunch of this and very little of this, and the constant is smaller than 1. Oh yeah. So another way to say it is, here it is. If the constant is bigger than 1, the forward reaction is favored, and I probably will make quite a few products. And the reverse is also true. If my constant is smaller than 1, then the backwards reaction is favored, and I'll probably favor having quite a bit more of the products. In writing these constant expressions, remember that the pure solids and pure liquids are somehow incorporated into the fold and into the constant number, so we're not allowing them to enter into our calculations. So if there is a pure solid and a pure liquid, I leave it out of the expression, or just put a 1 there as a multiplier. Oh yeah, there's nothing special that says we have to put mixtures together that are already in an equilibrium condition. So I might just throw some random mixture of gases or aqueous phase ions in a pot and say what will happen to it. Oops, I forgot my T right there. Shift. The reaction will shift in a way as to attain an equilibrium. And that's reflected by this thing, which looks exactly like K, except K was at an equilibrium, but Q is not necessarily, or we're suspecting that it's not at equilibrium. Alright, the exact same thing, and do that calculation. If I had, if I knew my numbers, the amounts of A and B and C and D, or whatever you have, put them in the expression, balancing the equation with little a, little b, little c, little d in blue, raise those to the power, and do a calculation for the reaction quotient. If that comes out bigger than K, that means I have too much of this and not enough of this, and that means the reaction will go backwards. If I have too much of this and not enough of that, and vice versa. If Q comes out smaller than K, then the forward will be favored, and the Q will grow in size up until the point where it equals KEQ. If the rare case, or hard to believe it's coincidental, would happen where Q is equal to K, then we are already in an equilibrium state. Le Chatelier's principle, very important. I imagine it might be on the final. I could state what Le Chatelier's principle is. It says that nature likes a balance, and if you adjust the balance, or if you do something to a system to stress it, add too much of one, not enough of another, nature will move in a direction to relieve that stress. She'll do whatever she can to go against it. Let's use this equation as an example. This is a kind of a summary or a hypothetical equilibrium of carbon dioxide gas, water liquid, sugar, a simple sugar, solid, and an oxygen gas. The delta H change in enthalpy, 2816 kilojoules. That means it's endothermic. This is not exothermic. If there was a negative here, right, that's more common. But being endothermic, I decided to go ahead and write my number on the left-hand side and treat it as a reactant. So inputting endothermic, this amount of energy into this and this, allows the formation of the equilibrium. So questions. How will this equilibrium shift if I increase the pressure of carbon dioxide? So in a way, I jack this way up, probably by adding a whole bunch of extra carbon dioxide. And now there's a knock on my door. Sorry. Must pause. Oh, I apologize. Where was I? Yes. Increasing the amount of carbon dioxide in an equilibrium balanced mixture would create too much of this reactant on the left, and therefore the Mother Nature, Le Chatelier would say that we'll shift this way to produce more of this and more of this. Shift it to the right. Decreasing the temperature would be like treating this number as some kind of crude measurement of energy or temperature. If I decrease this, and I know I'm treating that very loosely, but I'll just say that, decrease this, and Mother Nature will shift this way to try to make some more of that or increase the quantity on the left-hand side. Removing carbon dioxide, taking some or all of this out, would create an emptiness, a void, a vacancy, and nature would shift to the left to try to fill some of that in. Increasing the container volume is a very tricky one. Increasing the volume would decrease the pressure because the gases would have more room to roam around, decrease the pressure. So if I decrease the pressure, Mother Nature would like to would go against that and do what she could to increase the pressure. The only way forward to do that in a system of gases, would be to shift to a direction that would create more moles of gas to increase that pressure to go against what you did to the system, increasing the volume. But as it so happens, this side has 6 moles of gas, and this side has 6 moles of gas. Liquids and solids don't affect much. That's why I'm sort of ignoring these in a sense. And so the answer is no effect. Unfortunately, this system could not adjust to that decreased pressure. 6 moles of gas and 6 moles of gas. So if she shifted this way, it would still have 6 moles of gas, or if she shifted this way, it would still have 6 moles of gas. Oh yeah, that's another question I didn't write down here. What if I increase the amount of water a little bit or decrease this a little bit? And the answer is it wouldn't matter much as long as there's some there to maintain the equilibrium. What if I added some helium gas to this mixture? Well, that's a silly question. I don't see any helium gas at all listed. So indeed the answer is no effect. If you add something inert or something that's not going to react with something else present, it doesn't affect the equilibrium. Lastly, what if I added a catalyst to the mixture? Adding a catalyst might help it attain an equilibrium more quickly, but certainly doesn't shift the equilibrium one way or the other. Usually we think of a catalyst as bringing things forward more quickly, and indeed that may be true, but it doesn't affect the final equilibrium balanced mixture. Really the only thing that affects that constant is the pressure. The temperature. The temperature affects the equilibrium constant. I summarized all those down here for you, especially the long blah 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 about the volume. Goodness gracious. So take a look at that sometime again if you can. Common ion effect says that if I have an equilibrium set up and some ions and some species, this is a molecule in the water. This is vinegar, and it's a weak acid, so I could actually break out the buffer equation on this. I'll remind you of that in a second. But I did a little calculation and found out that vinegar dissociates on a small amount in a 0.1 molar solution of this based on that constant. But what if I didn't have this vinegar, this is the vinegar, in pure water so that it could do this freely and easily? What if I had this vinegar, call it 0.1 molar vinegar again, in a 0.21 molar sodium acetate solution? Well, this is a mess. This stuff gets in the way of this molecule, breaking apart, dissociating to create more of this and more of this. So instead of this being nothing in the beginning, this is jacked up to 0.21 molar, and that's 0.1 molar. And this one gets in the way, certainly, of this one dissociating to create any of this. Although if indeed I had no hydrogen ion, or very little hydrogen ion in the water, there would still be some of this breaking apart to give that. and that number decreases from 0.134% to 0.00086%, which is quite a bit smaller. Another example of the common ion effect is often described as that of slightly soluble salts like barium fluoride. And did a little calculation here. Oh yeah, remember that's a squared, but this unit of salt gives 2 fluoride ions, so that's kind of tricky. And lo and behold, this barium fluoride dissolves to the extent of 0.0075 moles per liter. But what if I wasn't trying to dissociate this barium fluoride into pure water? What if I was trying to dissociate this barium fluoride into sodium fluoride water? Just make up a number. I just made up a number, 0.22 molar. Sodium fluoride would dissolve pretty well. And so instead of just an X, or a 2X rather, this would be 0.22. Or we could set up an ice table for this, and you could convince yourself that this would increase a little bit from 0.22, but very, very, very small. How about something like 0.22 plus 0.000035 molar, give or take a little bit? And the key is that constant. That constant still has to be satisfied even if this number is fixed at a large amount. Oh, and by the way, that therefore means that this barium fluoride is much less soluble in sodium fluoride water. Acids and bases, oh my goodness, a can of worms. I don't have time for examples here and now, but I'll just show you the equations again. For the acid, for the base, for the Ka, for the Kb, for the pH, for the pOH. Definition of pH, definition of pOH. The sum must be 14. pKa, pKb, negative log, for any acid conjugate base pair. And for water, at 25 degrees Celsius, the pH is about 7. 10 negative 7, 10 negative 7, 10 negative 14 multiplied together. And lastly, for slightly soluble salts. I apologize, I feel badly just showing you these equations without working examples, but in a 15-minute video, who has time for that? Life's too short. So is YouTube. Too short. Need some long videos on that, baby. Alright, oh yeah, where am I at? For slightly soluble salts, where these salts, this metal-non-metal combo doesn't dissolve very well in water, these KSP numbers are very, very small, and they say that a little teeny bit of the salt dissolves in the water. If I have little m number of capital M ions, or little x number of capital X ions, the charges actually are reversed, plus x, plus little x, and minus little m. And again, these solubility product numbers are small, teeny tiny. If I'm curious as to whether precipitation might happen, I use the same thing as I did earlier, the reaction quotient, except it looks just the same as K. If I'm pouring a certain concentration of this with a certain concentration of this, and I consider my final ending concentrations of the two is per the total volume of solution, then I can use the Q again to say, is Q larger than KSP? If this is too big, then if this is too big, if this is too big, that means this is too much, and it'll go back this way, and I will see precipitation. And the opposite is also true. Whereas if I don't have that many, if this is very, very small, this is very, very small, and Q comes out very, very small, specifically smaller than the KSP, then all the solid remains dissolved. I see no precipitation, and voila. Gosh, that's what, 2 months of study in a nutshell in 14 minutes. Good luck studying, guys. Come to the reviews if you have time. I'd love to see you there.